All right, here goes our first video. I'm going to pick us up right where we had left off in class, and that was doing this one, show that 2 to the 1 over n goes to 1 for this sequence here. And again, we're using this idea that our sequence could be represented as a function where we're only plugging in discrete values of n. And so what we can do is let f of x equal 2 to the x, right? Because we have a 2 to the 1 over n. And we'll have the limit as n goes to infinity of 1 over n equals 0. Therefore, f of 1 over n will go to f of 0. And in that case, 2 to the 1 over n goes to 2 to the 0, which just means that we're going to 1. So 2 to the 1 over n goes to 1, which is what we were trying to show. All right. Next, we're going to move on doing some more with this same basic idea. Again, we're using the idea that we can replace what we're looking at with a function that's defined for a sequence, where with the sequence all we have to do is just put in discrete values of n and get back out our sequence from the function. And so if that is the case, so, we suppose f of x is a function defined for all x greater than or equal to n naught, and that the sequence an is a sequence of real numbers such that an equals f of n for n greater than or equal to n naught, then as the limit as n goes to infinity of a sub n equals L whenever the limit of f of x as x goes to infinity equals L. So therefore, we may differentiate to apply Hopital's rule. So I'm not sure if you remember that, but basically, if you have an indeterminate form for a limit, an indeterminate form, which was things like 0 over 0 or infinity over infinity, or infinity times 0, etc. If you have an indeterminate form, then we could take the derivative of the top and the bottom, and then the limit of the new resulting thing would have the same limit. But again, be careful. You're not doing the quotient rule. You're doing the derivative of the upper function, the numerator function divided by the derivative of the denominator function. So let's take a look at this one. Does a sequence whose nth term is an equals n plus 1 over n minus 1 to the nth converge? If so, we want to find that limit as n goes to infinity of a to the n. So limit as n goes to infinity of n plus 1 over n minus 1 to n is going to equal 1 to infinity. All right? But Hopital needs f of x over g of x. All right? And we're not kind of having that here. So what we can do is take the limit, right, equals limit as n goes to infinity, and what we'll do is do e to the natural log of n plus 1 over n minus 1 to the n power, and then we can bring that n out in front. This one right here can go out in front, and we'll get the limit as n goes to infinity of e to the n ln of n plus 1 over n minus 1. All right. So at this point, we can start looking at just what is in that. So at this point, we have an e to the x, which means, you know, if we look back to that last page, we can let f of x equal e to the x and do what we did on the last page now at this point. So we need to look at the limit of what the exponent is, the x. So we're going to go over and switch to looking at the limit as n goes to infinity of n natural log of n plus 1 over n minus 1. And this we can make into an actual fraction. So we can make this limit as n goes to infinity of the natural log of n plus 1 over n minus 1 divided by, and I'm going to take that n that was out front and make it 1 over n in the denominator. All right? And so at this point, we have something we can actually apply Hopital's rule to. So for the numerator, okay, we can do, so here we're going to apply Hopital, okay, and we can take the derivative of the natural log of n plus 1 over n minus 1. And when we do that, we get 1 over n plus 1 over n minus 1 times the derivative of what's on the inside. So that's outer and then inner. So times the derivative of what's on the inside, which I'm just going to go ahead and write as ddn of n plus 1 over n minus 1. That's going to require us to do, well, you can either make it a multiplication and do the product rule, or you can go ahead and just make it a, if you remember it, do the quotient rule. So I'm going to go ahead and just do quotient here. And so the derivative of this part over here ends up being n minus 1, right? The denominator times the derivative of what's on top, which will just be 1. And then minus what's on top, n plus 1, times the derivative of what's on the bottom. Derivative of what's on the bottom, again, is just 1. And then all divided by the denominator, n minus 1 squared. Okay? And at that point, we have an n minus 1 squared in the denominator, and we have an n minus 1 on the denominator. And so we can actually cancel out one of those. And then we have, you know, we can start looking at, we've got here, we have n minus 1 times 1, and then we have minus n plus 1 times 1. So this is going to be n minus 1 minus n minus 1 in the numerator over top of n plus 1 times n minus 1. In the numerator, the n's cancel, and we're going to end up with negative 2 over negative 2 over n squared minus 1. And then for the denominator over here, we have 1 over n. So the derivative of 1 over n with respect to n is just negative 1 over n squared. And so we can come back over here and put these both back in. Limit as n goes to infinity of this whole wonderful thing here. Let's get negative 2 over n squared minus 1. And then I'm going to, instead of dividing by negative 1 over n squared, I'm going to multiply by the reciprocal. So negative n squared over 1 is the reciprocal of negative 1 over n squared. And at that point, I can go ahead and actually start, you know, putting this together. Like the negatives will cancel, and The 1 will cancel, and we end up with the limit as n goes to infinity of 2n squared over n squared minus 1. And if you note now, we have an n squared and n squared, so the leading term has the same power for both of them. So they're the same order of polynomials there, which means that as we go out to infinity, that limit is just going to be the ratio of the leading coefficients. The leading coefficient on the top is a 2, because it's 2n squared, and a 1 on the bottom because of the n squared is just 1n squared, which means this is just 2. Therefore, we've got that limit. Our f of n times the natural log of n plus 1 over n minus 1 goes to f of 2, because that's what that goes to, and then a to the n is going to go to e squared. All right, so again, if you have to, go ahead and go back and look at that again, but there we go. It's going to e squared, because that's what our exponent went to. All right, so rewind, look at that again if you need to. I know that one was quite a lot all at once there, but let's move on. So some commonly occurring limits that you're going to want to know for this: the limit of the natural log of n over n as n goes to infinity. You're going to want to know this one is 0. This should make sense because the natural log function, if you look at it, is doing something like this, whereas just plain n is doing like this. It's going to get much, much larger than the other. Over here, we're doing the nth root of n, and this one is actually going to go to 1. Here, we're doing the limit as n goes to infinity of x to the 1 over n. This is also going to go to 1. I would expect these to be ones you memorized. And of course, this is for x greater than 0. And then next, x to the n, as n goes to infinity, is going to go to 0. Okay. And here we need the absolute value of x to be less than 1, which means x is greater than -1, less than 1, okay? And then that's going to be true. And then next we've got the limit as 1 plus x over n to the nth. It's going to go to e to the x. And if that looks familiar to you, then you should be be kind of proud of yourself, because that's actually the little formula that occurs when you start trying to calculate interest rates, and you start going toward an instantaneous instant rate. So you start with, like, I'm going to calculate it once a year, and then I'm going to compound it once a year, then compound it twice a year, compound it 4 times a year, 5 times a year, 100 times a year, 1,000,000 times a year. So you get to the point where you're compounding it instantaneously, and then you get e to the x there. And this is true for any fixed x. So if you've seen that kind of form there, that's where that comes from. And then here, x to the n over n factorial, again for a fixed x, is this one's going to equal 0. Okay? And those were ones that you're going to want to really make sure you're actually familiar with and be ready to do this. All right, so now what we're going to look at is some recursive definitions for these things. The first term or two of the sequence, along with a recursion formula for the remaining terms, is given. Write out the first 5 terms in the sequence. So basically what you're doing is taking previous values and plugging it back into itself to get the next one. If you've ever done any computer programming, they're recursive algorithms. I've never been a big fan of them, but it seems like you can always come up with a better, more efficient way than to use them. But sometimes they are kind of useful. So if we look here, we have a1 equals 1, and then they're telling us that in order to find a(n), we have to have the previous one, a(n minus 1. So in order to find a2, so let's say n equals 2, and write it a little better, sorry, n equals 2, we have to have the one before it, which is going to be a1. So a2 will equal a to the 2 minus 1 plus 1, which is a1 plus 1, which is just 1 plus 1, which is 2. And now that we have n2, we can do n3. And so a3 is going to be a3 minus 1 plus 1, which is a2 plus 1, which is 2 plus 1, which is just 3. And you can go on and keep doing these a4, a5, and do the same sort of thing, and you'll get 4 and 5 and so on and so forth. All right, so you're just kind of plugging previous ones into itself like that. For example, we can take a look at this next one here. This is going to give us a1 equals 1, and then an equals n times a to the n minus 1. So a2 is going to equal n, so this is for n equals 2, okay? It's going to equal 2 times a1, the previous one. Well, a1 was just 1, so this is 2 times 1, which is 2. And a3 is going to equal 3 times a2, which is 3 times 2. And if we wanted to write this out longer, remember a2 was 2 times 1, so this was 6. And if you want to look at a4, it's 4 times a3. And I'm writing it like this on purpose, so just give me a second here. 4 times a3 is 4 times 6, but it was also written as 3 times 2 times 1 right above it. So 4 times 3 times 2 times 1, and that's going to just be 24. And I'm going to do one more, and you should start to notice what this actually is. This will be 5 times a4, and remember a4 was 4 times 3 times 2 times 1. So this is 5 times 4 times 3 times 2 times 1, or 5 times 24, which is 120. And if you haven't noticed this already, this is n factorial. This is 2 times 1, this is 3 times 2 times 1, this is 4 times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1. The next one would be 6 times 5 times 4 times 3 times 2 times 1. So this is actually a recursive way to do factorials. Okay, so let's take a look at one more here. We'll look at C. And a1 equals 1, a2 also equals 1, and a to the n plus 1 is going to be the previous one plus the one before it. So our next term, a to the n plus 1, is going to be the sum. It's going to be the sum of the previous two terms. And if you don't recognize that, that is actually a Fibonacci sequence. And if anybody's really super interested, you ought to look up the Fibonacci sequence and its relationship to the golden ratio. It's pretty interesting, and if you're super interested and you can't find anything really much on it, just let me know and I'll maybe make you up a fun little video about how it relates. But you got to take linear algebra at some point, and when you do, you can actually do some linear algebra stuff and get the golden ratio out of the Fibonacci sequence. So anyway, let's keep going here. So this is n equals 2 right there. N equals 2 is that one right there, and n equals 1 is that one right there. And so we're going to start with n equals 3, or a3, and that's going to be a 2 plus a 1, and that's just going to be 2 plus 1, which is 3. And then, oh, I'm sorry, that one's not 2. That's going to be 1 plus 1, sorry. That's 1, that's going to be 1 plus 1, that's 2. And then a4 is going to be a3 plus a1, which will be 2 plus 1, which is 3, and a5 is going to be a4 plus a3, and that's going to be 3 plus that's going to be 3 plus 2, which is 5, and then the next one would be 5 plus 3, which is 8, and then 8 plus 5, which is 13, and 8 plus 13, which is 21, and 13 plus 21, which is 34, and so on and so forth, where you just keep adding the previous two together. Okay? So there are some recursive versions of some sequences. So now let's look at a bounded sequences. What does that mean? Well, a bounded sequence, or a sequence, is bounded from above if there exists another number m such that a sub n is always less than or equal to m. In other words, for all n, that it never goes above that. And if that is the case, the number m is called, well, I don't like the word the, it's called an upper bound for an. If m is an upper bound for an, but no number less than m is an upper bound, in other words, it's the smallest upper bound, because if you think about it, if say 4 is an upper bound, then so is 5, and so is 6, and so is a million, and all that stuff. That's why I changed that word to, that's why I changed this up here to an upper bound. But if it's the lowest upper bound, there's no other upper bound that's greater than all your numbers there's no upper bound that is greater than all the members of your sequence, but also smaller than whatever upper bound you're looking at, then m is the least upper bound, and that's the one you're going to typically mostly be interested in. So if we look at this example here, n over n plus 1, that gives you 1/2, and then 2, not plus, sorry, starting series already, 1/2, 2/3, 3/4, so just plugging in n, it's always going to be that way, 4/5, so on and so forth. And if you notice that it's getting closer and closer, but it's never going to reach 1. And in fact, 1 is the least upper bound for that. It'll keep getting really, really close. You'll end up with, 99 over 100 and so on and so forth. And just get really, 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 really close. A million over 1,000,001, that's really close to 1, but it's never quite getting there. So if this is 1 right here, it's just never gonna ever cross that line. It's never even gonna quite reach it. All right, but just keep getting closer and closer to it. Like if it was a function, we could replace that with, then it would asymptote to that 1, if you want to think of it that way. Next, a sequence is bounded from below this time if there exists a number m such that, doing lowercase m, is always less than or equal to a sub n for any n. The number m is, again, a lower bound for a n. If m is a lower bound for the set a n, but no number greater than m is an upper bound for a n, then m is that should be the lowercase m's, I think we were doing, but I guess I shouldn't have made a lowercase m. I'll go back to the capital up here, sorry. Then, no, that should be a lowercase bound. What am I doing? Sorry about that. Then m is the greatest lower bound. So this should have been a little m and a little m. Sorry, there, that's the correction to make. I made the wrong correction. All right, it's the greatest lower bound for our sequence. So if an is bounded from above or below, then an is bounded. If an is not bounded, then we say that an is an unbounded sequence, okay? But you can see here in the figure that we've got it bounded on the top and the bottom there. It's never going to go above or below the little m. Never going to go below the little m and above the big M. All right? So let's take a look at monotonic sequence. This is, all right, this is a sequence. A set of an is non-decreasing if an is less than an plus 1. So for all n, in other words, the next term in the sequence is always greater than the previous. That is, a1 is less than a2, which is less than a3, which is less than a4, so on and so forth. And the sequence is non-increasing if an is always greater than the next one for all, or equal to, for all n. The sequence is monotonic if it is neither non-decreasing or non-increasing. So monotonic, non-decreasing, non-increasing. So here we go. The monotonic sequence theorem. If a sequence set A of all an is both bounded and monotonic, then the sequence converges. All right. So it's not non-decreasing and it's not non-increasing, and it's is bounded. Then we know that it will converge. So that's the basic idea here. Yep. So if you're looking at that picture, we're getting bounded, and it's also not cutting back down, so it's going to converge. If that kind of makes sense. So it's not gonna. It's, in other words, we might have an upper bound, but if these start going back down like this, then it's diverging. So it has to both be bounded on the top and constantly increasing, but not increasing past that upper limit. All right, so let's try this. Show that n over n plus 1 converges. So n over n plus 1. This is going to give us 1/2, 1/2, 2/3, 3/4, so on and so forth. So this is monotonically and it's non-decreasing. All right, that's what we were saying up above here. It's monotonic because it's non-decreasing, and non-decreasing because every version is bigger than the previous. All right, this keeps getting larger and larger, closer and closer to 1. And it's bounded, as we talked about previously, by m equals 1. If that's the case, that means therefore by our monotonic sequence theorem, and I'm going to write that as MST, by MST, n over n plus 1, our set n over n plus 1, converges. Okay, that is it for this video, and I'll see you in the next one.